On paper, x86 is dead. Not because it's slow, not because it's outdated, but because the architecture itself has reached the end of what it can physically do. And yet, we are still patching it. APX, new register models, speculative fixes, microarchitectural band-aids, all to keep a 50 years old design alive a little longer. Today I want to show you why x86 is technically finished and why the industry still can't walk away from it. This isn't nostalgia, it's the uncomfortable reality of modern computing. To understand the limits of x86, you don't need a PhD in microarchitecture. You don't need a deep dive into pipeline diagrams or front-end bottlenecks. You just need to look at what happens when you ask the architecture to keep 24 live variables inside a tight loop. That's it. One simple function, and the whole story unfolds. Here's the function. 24 independent 64 bits variable, all updated inside a loop, all alive at the same time, all needed for the final result. This is not artificial, this is exactly the kind of pressure modern workloads create. Cryptography, compression, simulation, JIT generate code, vectorized pipelines, state machines, and on x86 this is enough to break the architecture. Let's compile it with -02 on x86. Immediately the compiler runs out of registers, not because the compiler is bad, not because the code is weird, but because x86 simply doesn't have enough general purpose registers. So what happens? Spilling. Every time the architecture runs out of space, the compiler pushes values to the stack over and over. This register pressure, this is the architecture suffocating, this is the cost of ISA design for the 70s and stretched far beyond its original intent. And remember, every spill is a memory access, every memory access is latency, and latency is the enemy of throughput. Now let's compile the exact same function with -02, -mapxf. Suddenly the assembly looks cleaner. Fewer spills, fewer stack touches, more values stay in register. Why? Because APX gives x86 what is always lacked: more general purpose registers. And yes, it helps, it absolutely helps. But look closely, the structure of the code hasn't changed, the dependencies haven't changed, the instruction density hasn't changed. The front end still has not decoded the same legacy format. The architecture is still the architecture. APX reduces the symptoms, it doesn't cure the disease. This is the part people don't like to hear. The problem isn't the compiler, the problem isn't the microarchitecture, the problem isn't the silicon, the problem is the ISA. x86 was never designed for dozens of live variables, deep dependency chains, wide pipelines, modern compiler strategies, high ILP workloads, massive register files. So every generation we patch it. New prefixes, new encodings, new register model, new micro-op tricks, new speculative fixes, new front-end workarounds. APX is just the latest layer on top of a structure that was never meant to hold this much weight. If x86 is technically finished, why does the world still run on it? Because replacing x86 is harder than fixing it. The ecosystem is enormous. Operative system, hypervisors, virtual machines, container runtimes, cloud orchestration, decades of software, billions of lines of code, performance-critical libraries, vendor-specific intrinsics. You can't migrate is overnight. You can rewrite the word. You can break compatibility and global scale. So we patch, we extend, we stretch, we kept the architecture alive because the cost of replacing it is higher than the cost of maintaining it. x86 is technically finished. APX buys it time, but the architecture is what it is. We are living in the gap between the architecture we have and the architecture we need, and the gap is where the real story of modern computing is happening.